Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence.
Hey everyone, excited to dive into this paper today. Looks like we're tackling some pretty fundamental issues with memory and sequence processing in AI.
Definitely. Long sequence memory is a huge bottleneck. Current models struggle to maintain information over extended periods. So anything that addresses that is worth a look.
Absolutely. And the title, Long Sequence Memory with Temporal Kernels and Dense Hopfield Functionals, it already suggests some interesting approaches. Temporal kernels, dense Hopfield networks. Sounds like we're moving beyond vanilla recurrent networks.
All right, so let's jump in. What particularly stood out to you guys from the initial read-through? What caught your eye?
For me, it's the potential of combining these different mechanisms. Temporal kernels offer a way to capture time dependencies in the data, right? And Hopfield networks, well, they're known for their pattern completion abilities and robustness to noise.
Right? The Hopfield networks acting as a kind of content addressable memory, allowing the system to retrieve information based on similarity rather than just location.
Yeah, exactly. Think of it like this. If you're trying to remember a conversation you had last week, you don't just recall it word for word from a specific storage slot in your brain. You remember the gist of it, the key themes, and then you fill in the gaps. Hopfield networks are kind of like that gist generator.
That's a great analogy. So how do these temporal kernels play into that? Are they helping to structure the information being fed into the Hopfield network?
That's how I understand it. The temporal kernels are essentially extracting relevant features from the input sequence over time. They're encoding the temporal relationships between elements, so the Hopfield network receives a more structured and meaningful representation.
Okay, I see. So instead of just throwing raw data at the Hopfield network, the kernels pre-process it to highlight the important temporal dynamics. That makes sense.
And that pre-processing is crucial, I think. Otherwise, the Hopfield network would just get overwhelmed by the sheer amount of data. This helps to focus its attention on the relevant patterns. It's like giving it a map instead of just dropping it in the middle of the forest.
So let's dig a little deeper into the temporal kernels themselves. What kind of kernels are they using? Are we talking about simple moving averages or something more sophisticated?
From what I gathered, they're using more complex, learned kernels. So the network isn't just averaging over a fixed window of time. It's actually learning which timescales are most important for the task at hand. That's where the real power comes in, I think.
Right, adaptive kernels, that's a key point. It allows the system to adjust its temporal receptive field based on the specific characteristics of the input sequence.
Exactly. Think about language. Sometimes you need to pay attention to the immediately preceding words to understand the current word. Other times you need to consider the entire sentence, or even the entire paragraph. Learned kernels can adapt to those different timescales.
Okay, that makes sense. So the kernels are learning to extract features at different temporal resolutions, and then these features are fed into the dense Hopfield network. What does dense mean in this context? Is it just referring to the connectivity of the network?
Yeah, that's my understanding. Traditional Hopfield networks often have sparse connections, meaning each neuron is only connected to a small subset of the other neurons. A dense Hopfield network, on the other hand, has much more extensive connectivity. Each neuron is connected to a larger proportion of the network.
And that increased connectivity allows for more complex pattern storage and retrieval, right? It increases the network's capacity to remember and recall different states.
Precisely. More connections, more potential attractors. Each attractor corresponds to a stored memory. So, a denser network can store more memories and be more robust to noisy inputs.
Okay, so we have temporal kernels learning to extract relevant features from the input sequence, and then a dense Hopfield network using those features to store and retrieve memories. How does this compare to more traditional approaches to long sequence memory, like LSTMs or transformers?
That's the million-dollar question. LSTMs and transformers have been the dominant architectures for sequence processing for years now. They're incredibly powerful, but they also have their limitations. Vanishing gradients, computational complexity, difficulty with very long sequences.
Right? And transformers, while powerful, require a lot of computational resources and data to train effectively. They're not always the most efficient solution, especially for resource-constrained applications.
And both LSTMs and transformers can be a bit of a black box. It's often difficult to understand exactly why they're making the decisions they're making. The combination of temporal kernels and Hopfield networks might offer a more interpretable alternative.
Interesting. So this approach potentially offers benefits in terms of interpretability and efficiency. But what about performance? Does it actually outperform LSTMs or transformers on long sequence memory tasks?
Well, that's what the paper claims, right? They report results on several benchmark datasets, and they show that their approach achieves competitive, and in some cases superior, performance compared to state-of-the-art LSTMs and transformers.
But, and this is a big but, we always need to be careful about benchmark comparisons. The devil's in the details. What data sets were they using? How were the models trained? What were the hyperparameters? All of those things can significantly impact the results.
Exactly. And even if they do achieve better performance on certain benchmarks, that doesn't necessarily mean they're solving the underlying problem of long sequence memory. It could just be that their architecture is better suited to those specific datasets.
Okay, valid points. So let's assume for a moment that the performance claims are valid. What are some potential real-world applications of this technology? Where could this kind of long sequence memory be particularly useful?
Oh, there are tons of possibilities. Think about video analysis. Being able to track objects and events over long periods of time is crucial for things like surveillance, autonomous driving, and robotics.
Or consider medical diagnosis. Analyzing long-term patient data, like electronic health records, to identify patterns and predict potential health problems. That requires the ability to maintain information over years, even decades.
And don't forget about financial modeling. Predicting market trends requires analyzing vast amounts of historical data, identifying subtle patterns and correlations that might not be apparent in the short term.
Those are all great examples. So from video analysis to medical diagnosis to financial modeling, long sequence memory has the potential to revolutionize a wide range of industries. But what are the limitations of this particular approach? What are the challenges that still need to be addressed?
Well, scalability is always a concern. Hopfield networks, in particular, can become computationally expensive as the number of neurons increases. So, scaling this approach to handle truly massive datasets could be a challenge.
And interpretability, while potentially better than LSTMs or transformers, is still an issue. Understanding why the network is making the decisions it's making is crucial for building trust and ensuring safety.
And I think the biggest challenge is generalization. Can this approach generalize to new tasks and new environments? Or is it just overfitting to the specific datasets it was trained on?
Right. The holy grail of AI, generalization. So let's shift gears a bit and talk about future research directions. If you were to take this work and build upon it, what would you focus on?
I'd be interested in exploring different types of temporal kernels. Are there other kernel functions that might be better suited to specific types of data? Could we learn the kernel structure itself, rather than just the kernel parameters?
I'd focus on improving the interpretability of the Hopfield network. Can we develop techniques for visualizing the attractors or for understanding how the network is representing information? Maybe even integrating symbolic reasoning into the network somehow.
I'd want to investigate the relationship between this approach and spatiotemporal reasoning. Can we extend this architecture to handle data that has both temporal and spatial components? Think about video games, for example. The agent needs to remember what happened in the past and also understand its current spatial environment.
Those are all excellent directions. From my perspective, I'm really interested in exploring the connection to multi-agent systems. The brain's ability to rapidly adjust its responses to context suggests a potential model for building more robust and responsive multi-agent systems. If we can understand how the brain achieves this using long sequence memory, it could revolutionize multi-agent coordination.
That's a fascinating point. Thinking about multi-agent systems, the ability to remember and reason about the actions of other agents over time, is crucial for effective collaboration.
Yes, and applying a neurosymbolic approach here could offer a path to bridge the gap between purely data-driven models and the need for more robust and interpretable collaboration strategies in multi-agent systems. We can get safe AGI.
It could be useful to explore the spatiotemporal component of multi-agent intelligence, observing how these systems struggle with the transition from one coordinate system to another. It might help to identify crucial limitations that we haven't yet understood.
Exactly. Imagine each agent having its own internal representation of the world, its own coordinate system, and then they need to coordinate their actions in a shared environment. How do they translate between their internal representations? That's where the real challenge lies.
It almost sounds like a problem of translation, like each agent is speaking a different language. And the system needs to learn how to translate between those languages in real time.
Or like a group of people trying to assemble a piece of furniture without a common instruction manual. They each have their own understanding of the instructions, and they need to figure out how to work together to achieve a common goal.
And the key is to do it efficiently and robustly. You don't want the system to break down every time one of the agents makes a mistake or encounters an unexpected situation. You need a system that can adapt and learn and continue to function even in the face of adversity.
That's right. So building on this paper, I think there's a huge opportunity to explore the intersection of long sequence memory, multi-agent systems, and neuroscience. How can we leverage the principles of brain plasticity and neural synchronization to build more robust and adaptable AI systems?
And what about the role of attention? How does the brain selectively attend to relevant information in a complex environment? Can we incorporate attention mechanisms into these AI systems to improve their ability to focus on the most important aspects of the task at hand?
Yes, and how can we design attention mechanisms that are more interpretable and controllable? Instead of just blindly following the attention weights, can we understand why the system is attending to certain features and not others?
And how can we represent uncertainty in these systems? The real world is inherently uncertain. How can we build AI systems that can reason about uncertainty and make decisions even when they don't have all the information?
These are all incredibly important questions, and I think this paper provides a valuable starting point for exploring these issues. By combining temporal kernels and dense Hopfield networks, they've shown that it's possible to build AI systems that can handle long sequence memory more effectively than traditional approaches.
I agree. This is definitely a promising direction, and I'm excited to see how this research evolves in the coming years. I think it could have a significant impact on a wide range of applications, from robotics to healthcare to finance.
Agreed. While I remain skeptical about the purely data-driven approach, I acknowledge the importance of addressing long sequence memory limitations. I am hopeful that the right balance of symbolic reasoning and learning may allow AI to pass these benchmarks.
Definitely food for thought. Now that we've gone into that, there are some concerns about the development of AGI that I need to share with you. But maybe we can talk about this in another episode.
Well, that's about all the time we have for today. Thanks for joining us on Cognitive Spirals. We'll be back next week with another deep dive into the latest research on consciousness, cognition, and machine intelligence.
Yeah, thanks for listening, everyone.
Bye.
See you next time.